In this section, we're going to create follow the leader effects, rain effects, waterfall effects, and dissolving effects for texture, static mesh, and skeletal mesh. We'll first start with going over all the basic things that you need to know for creating a custom Niagara module. Then, using the knowledge that we have on Niagara variables, namespaces, we're going to create this follow the leader effects. Then, with a little bit of vector math, we're going to create a more advanced version of it. And using what we've learned, we'll look at how we can create this rain effects. We'll first dive into the Fresnel effect and use it to help us to create a liquid master material. Then, using collision event, we're going to generate different rain splashes, ripples, and handle the particles spawn on the slope using collision normal and dot product. You're also going to learn how to create custom Niagara enums and how to use our custom enum in our custom module. Then we'll look at how we can use all the skills we have to create the waterfall effects. We'll first start with creating a waterfall mesh, then a waterfall master material. And using the caustic textures that we created, we're going to create the waterfall we want. After these effects, we're going to look into how to create different dissolving effects for textures, static mesh, and combine all of this with distance field to help us to create this dynamic dissolve effects for skeletal mesh. There's a lot of cool stuff in this section. When you are ready, let's dive right in. Welcome! Starting from this lecture, we'll look at how we can use custom Niagara modules to help us to create VFX. Before we do that, I like to create a new map for it. So go inside of my maps folder, and in here, I'm going to create a new map. So go to File, click New Level, and I'm going to select this basic, click Create. Then go to File, click Save Current Level As, and I'm going to rename this map to Custom Niagara Module. Then click Save. And the next thing we need to do, same as before, we need to set up the demo room, the demo display, get the scale correct, use post-process volume to lock the exposure. I'm gonna quick time-lapse it, as I'm sure you are already familiar enough with it. Alright, now I have my demo room ready, so if you'd like to catch up with me, you can pause the video now and set up the demo room yourself. Welcome back! Now let's look at how we can create a custom Niagara module for our VFX. So to do that, I'm gonna go to the Niagara folder. Inside of it, I'm gonna create a new folder. So for this one, I'm gonna call it Custom Niagara Module. Then double click to open it, and inside of it I'm going to create another folder. I'm going to rename this folder to Simple Custom Module. So we are going to start with some simple custom Niagara modules and double click to open it. So inside of it I'm going to create a Niagara system, select new system from selected emitters, then go down to Simple Sprite Burst, click Finish. I'm going to keep its name a default for now, and I will change that later. Alright, I'm going to double click to open this Niagara system. So we want to create a custom module. Where do we start? So for custom Niagara modules, there are two ways to create one. The fastest and the most direct way is do it inside of Niagara emitter. So if you click the app button here and you type in Scratchpad module, and you can see it's right there. By clicking it, we'll get a new custom Niagara module. And before we do that, it's important that you know which stage you want to put the module under. That's why it's very important for us to understand the basics here. Otherwise, we won't even know how often our custom module will be run. So in this case, I'm going to put my new custom module under the particle spawn stage. So this module will be called once per particle when it's spawned. So click Add again and type in Scratchpad and press enter. And you can see this is where I get a new interface for custom Niagara modules. And you can see inside of it, we have pins to connect. On the right here, there are many different properties that we can set for this Niagara module. We are not going to go into them right now. Instead, we are only going to be focusing on what's going on in here. So you can see in here, I'm gonna first click pause in here. So instead of this graph, very similar as Blueprint, you can see we can drag out pins and we can place a new node in here. Now you might be thinking, well, is this Blueprint? Actually, it's not. So this is Blueprint, and this is the graph for Niagara module. And the reason why you are feeling they are very similar is they're both using the graph paradigm. So inside of it, we can use nodes, we can connect pins to help us to write code. But unlike Blueprint, where we use nodes and pins to write C++ code, for Niagara module, inside of this graph, the code we are writing is something called HLSL. So in short for high-level shading language. This is the same language for our material editor. So when operating inside of our material editor, we are writing this code. But no matter it's C++ or HLSL, it doesn't matter which language we are using, we still have the same coding principle. And that's something we can use in other languages as well. So I'm sure you already noticed that the graph for a Niagara module is quite different from Blueprint. In order to write code inside of it, where do we even begin? Well, to do that, we first need to understand the parameters inside of the Niagara. So you can see, after this red node, we have this node, it's called map get. And the map here stands for the parameter map. And for each of the emitter, it has its own parameter map. And inside of it, we can see something like this. So go back to my Niagara system. I'm going to go back to my system overview. So you can go to the top and click this system overview. And now I'm going to select the simple sprite burst and go to the left. So under the parameters tab, you can see this is the parameter map that I'm talking about. And there are quite a lot out there. So we have something called system attributes, emitter attributes, particle attributes, and even some module outputs. If this is the first time that you look at them, it may feel quite intimidating, but actually it's not. They can all be categorized into a few types. And the thing that Niagara uses to categorize them is something called namespace. So this is its namespace. If you're from the programming background, you may find this word very familiar. And if you are not, don't worry, this is actually quite simple. So you can see we have many namespaces here. We have something like system, emitter, protocols. Why do we need this? Well, in programming, the only reason that we want to use namespace is we want to distinguish the variables that have the same name. So take system, emitter, and particles for example. So all these three namespaces, they have one thing in common. So they all have one variable and it's called age. So now we don't have this namespace. How do we know what type of age that we are talking about? So when we use the variable age, are we referring to the system's age, or the emitter's age, or the particle's age? There's just no way to know. And that's where a namespace comes in. So in text, it will be written in something like this. So it will be system.age, emitter.age, and particles.age. And these are all the namespaces for all the variables inside of a Niagara emitter. And after knowing that, let's look at this parameter map again. So if I scroll up, you can see for this system attribute, so these are all the variables under the namespace system. You can see it has a variable, it's called age. And inside of this emitter attributes, it also has a variable called age. And for particle attributes, we have the same thing. So that's the first important thing that you need to know when creating a custom Niagara module. All the variables can be categorized by different namespaces. But how do we actually understand these variables? You can see for these particle attributes, inside of it, there are a lot of variables. Well, these are actually the things that we've been manipulating the whole time. We just didn't know they exist. Under the particle namespace, we have different variables like age, color, lifetime, position, and something like normalized age. So these are all the things that we use to control the particles. In other words, we've been setting these particles using existing Niagara modules. So take this module for example. This is our initialized particle module, and we've used this many times already. So after we bring out this module and we add it to a Niagara emitter, what this module will do is it will set all the parameters needed for us. And in Niagara is something called parameter writes. And we can quickly figure out what parameters a module is currently writing to. So if I go to this initialized particle and go to the right, you can see there's this view options in here. And in here, we have one option that says show parameter writes. After we click it, you can see we have one more drop down in here. If I click this drop down, so these are all the parameters this module is writing to. You can see it's writing to this color parameter, lifetime parameter, mask, position, sprite size. And how we are controlling these parameters is through all these inputs. So the lifetime here, this will directly write to this parameter lifetime. The color here will be writing to the particles.color in here. And same thing for this sprite size. We will be writing the data to this parameter. All the modules in here, they will be writing data to certain parameters that's predefined inside of these modules. And by using the inputs it has, we can change all the parameters however we like. Alright, now that you know namespace, parameter map, and what the module inside of Niagara is doing, let's look at how we can use all of that to help us to create our own module. So for custom Niagara module, we have this node, it's called map_get, and we have this node, it's called map_set. So the data flows from map_get to map_set. So we can get a value from the parameter map, then use that to set another value inside of the parameter map, as simple as that. So now I want to create a simple module. So I want this module to override the particle's lifetime. Well, to do that, for the input here, we'll need to create a float. And I'm gonna name it to something like lifetime. And what this parameter needs to write to would be the lifetime of the particle. And by using this setup, we can change the particle's lifetime in a custom module. So let's look at how we can do this. Go back to my Niagara system. I'm gonna go back to my Scratch module. So you can see here we have map_get and map_set. So for the map_get in here, I'm gonna click this add button. Then I'm gonna type in float. So you can see by default, when we create a new variable, its namespace will be input. So same as other modules, this will be something that we can see on the right in here. So I'm going to rename this new float to new lifetime. Then I'm going to use this value to set an existing parameter inside of our parameter map. So we can click this add button to add an existing parameter to this map set. And if you click this drop down called parameters, you can see inside of it, these are all the parameters belong to the namespace particles. And the parameter that I want to set is here. So particles.lifetime. I'm going to bring it out, then I'm going to connect this pin to here. As simple as that. Now we can set the particle's lifetime in our custom module. Alright, and there's one last thing that I want to do. So same as blueprint, we need to click compile constantly. For custom Niagara module, we need to do the same thing. And if you go to the top in here, you can see there's this apply scratch. So this will apply all the changes that we've made inside of this custom Niagara module. So I'm going to click this button, then go back to my system overview. And you can see here, this is my custom module. And currently, this is called Scratch module. That's not a very good name. And we can rename it by going to desktop local modules in here. And this is where we can rename this module. So by creating a Scratchpad module, it will only be visible to the emitter where it is created. So keep that in mind. Later, I'm going to show you a different way to create custom Niagara module that can be visible to all the emitters for our Niagara. So for now, I'm just simply going to rename this local module to nms_override lifetime. So the full name for a custom Niagara module is called Niagara Modular Script. So NMS is in short for that. Alright, I'm going to go back to my system overview. And I'm going to click this module. And you can see we have one input. It's called new lifetime. And if I click this drop down in here, you can see it's writing to this particle.lifetime. Alright, now I'm going to change its lifetime to something like 1 second and click play in here. And this is what we are seeing. Since this custom module is under this initialized particle, so the lifetime we set here will override the lifetime inside of here. So now if I change this lifetime to 0, this won't affect this particle's lifetime. Because if you recall, everything gets run from top down inside of a Niagara emitter. And it's time for a challenge. So challenge is, same as I did, I'd like you to create a custom Niagara module that changes lifetime. If you still feel a bit lost about parameter map, namespace, feel free to refer back to the video for help. And after this override lifetime module, I'd like you to create another one, and I want this one to directly change the particle's velocity. So in order to achieve this, think about what function inputs you need and what variables inside of the parameter map you need to set. Alright, pause the video now and give this a go. I'll come back if you need help. Welcome back. How's that? Did you successfully create another custom Niagara module? Don't worry if you run into any issues. Let's look at how it can be done. So the module that I'm creating will be overriding the particle's velocity, and I only want it to be run once per particle when they are spawned. So I'm going to create another local module under the particle spawn stage. So I'm going to click this add button, and I'm going to type scratchpad and press enter to add a new scratchpad module. First thing, I'm going to rename this module. So I'm going to call it MMS underscore add velocity simple. Alright, for this map get, I'm going to create a new function input. Since the parameter we are changing is velocity, the function input we need will be a vector. So I'm going to type in vector, and I'm going to select this one. So for this input vector, I'm going to change its name to velocity axis. So this will be the direction of our velocity, and I'm going to create another variable. So for this one, it will be a float. If you recall, for velocity, we need two pieces of information, its direction and its speed. So this will be my speed. And I'm going to call this velocity speed scale. Alright, I'm going to combine these two values together. So this will be the new velocity for my particle. So I'm going to drag out this pin, and I'm going to use a multiply node. And I'm going to multiply the axis with the speed scale and use this value to set the existing parameter, which will be something under the core parameters. And if you go to here, you can see there's this parameter called particles.velocity. And this is the one that I want to set. So I'm going to select it, then connect this value to here. Alright, that's pretty much it. Then I'm going to go to the top and click apply scratch and go back to my system overview. You can see now, this is the module that I just created. I'm going to select it. And in here, I have two function inputs, the velocity axis and the velocity speed scale. And the rest is the same as adjusting the existing module's input. So for example, we can click this drop down here to change this input from a static one to a dynamic one. So maybe here, I want a random vector. And for the velocity speed scale, I'm going to give it a default value, something like 50. And you can see now, my particle is moving in my viewport. And this is a completely random velocity. And if I click this drop down for parameter writes, you can see it's writing to the particle's velocity. And if a random vector is not what you want, you can reset this value and give it a hard-coded value. So for example, a value of 1 for the x. So the particle will be moving along the x-axis. Alright, the last thing that I want to do, I want to change this emitter state. So I want the loop behavior here to be infinite. And I like to drag out this to my level. So go back to my level. I'm going to rename this Niagara system. So I'm going to call it NS underscore simple module. Then I'm going to drag out this Niagara system in my level and press G to hide all the icons. And now you can see this is what I get. And I'm going to change the text on the demo display. So click it. I'm going to change the title to be something like simple custom modules. And for the description text, I'm going to add one new paragraph. And I'm going to type in custom modules for override particle lifetime and add velocity simple, and change the scale to something like 20. And that's pretty much it. In this lecture, we went over the basic concept for Niagara module, and we also went through the parameter map and all those different namespaces, and we also talked about the module and parameter rights. We've covered quite a lot of stuff in this lecture, so feel free to write down anything that you think are important on the demo display, and I'll see you in the next lecture. Welcome! In the last lecture, we talked about the Niagara module, and we also went through the concept of namespace and parameter map. Using what we've learned, we've created our own custom Niagara modules. So this is what we have achieved so far. And now with the understanding that we have, we can create something much more advanced. And the next VFX that I'm going to create is something called follow the leader. So as the name suggests, the thing that I'm going for is I want some particles to follow other particles. If we can do that, we can create some really cool VFX. So let's look at how it can be done. First, I'm going to duplicate this demo display. And I'm going to delete this paragraph and change its title to follow the leader simple. And go back to my custom Niagara module folder. I'm going to create another folder. I'm going to call this one follow the leader, and double click to open it. I'm going to create a Niagara system. So select this simple sprite burst as the starting emitter, click finish. I'm going to rename this to ns_follow the leader simple, and double click to open it. So in order for this to work, apparently we need two emitters. One will be the leader, one will be the follower. So I'm going to first create my leader. I'm going to rename this emitter to leader. And in order to make it a bit more interesting, I'm going to give it more particles and give it some simple forces modules. So first, I'm going to delete this spawn burst instantaneous and use spawn rate instead. Give it a default number of 10. I think that's more than enough. And go down to initialize particle. So for its lifetime, it doesn't need to be very long. I think a value between 0.5 and 0.8 will work. And I'm going to give it a simple color, so something bluish, and give it a default value of 10. So a bit brighter, then click OK. Then for the sprite size mode, give it a random value, so somewhere between 30 and 40. And I'm also going to break its spawn location. So use the module shape location. And for the sphere radius, I think I'm going to give it a radius of 150 units. Alright, and under the particle update stage, the first force module I'm gonna use would be vortex velocity. I hope you're already familiar enough with this module. I'm gonna change this velocity amount to something like 2000, and velocity axis, give it a value of 5 for the z. Now you can see my particles are rotating. Then I'm also gonna use another module, so current noise force, something we've used many times as well. The noise strength, give it a random value, so somewhere between 1000 and 1500. There are no specific reasons for me to use specific values. Feel free to try out your own values, and I think I'm going to drag it a little bit. So give this drag a random value, somewhere between 1 and 2 would be enough, I think. And I'm going to change its emitter state from once to infinite. And that's all the things that I want to set for my leader. Alright, next emitter, we'll need a follower. So right mouse button click to add an emitter. And I'm going to go to simple sprite burst. I'm going to rename this emitter to follower. So for this follower, inside of this sim target, I'm going to change it to GPU compute sim and change it to fixed bounds. Emitter state, change it to infinite. And delete spawn burst instantaneous, use spawn rate instead. So for this one, I'm going to be spawning a lot of particles. So for the spawn rate, I'm going to give it a value of 8000. And now we have a lot of particles in our viewport. So for its lifetime, I'm going to give it a random value, somewhere between 0.5 and 0.8. For its color, give it something reddish and change its value to 10. For the sprite size mode, I'm going to lower it down quite a bit, to something like 5 units, and break its spawn location. So use shape location. And for the sphere radius here, so the effect that I'm going for will be something chaotic. You'll know what I'm talking about very soon. So for this sphere radius, I'm going to give it a very low value, something like 5. And then, same as our leader, I'm going to give it some simple forces module. So the first one will be current noise force. Noise strength, give it a value of 1000. Now you can see this is what I get. And also, I'm going to give it the module vortex velocity. The velocity amount, give it a value of 1000. And lastly, I'm going to use the module gravity force. And I think I want to lower the gravity force down. So instead of negative 980, lower it down to negative 100. And you can see this is what I get. And these will be my followers. So these are the two emitters that we've created so far. Let's think about that. In order to achieve what we want, what do we actually need? So we have a leading emitter and a following emitter in here. But how do we actually allow these particles to follow these particles? Well, to do that, we'll need something that's called attributes reader. In other words, this emitter needs to be pulling data from this emitter, and the data that we need to get is the particle.position. So in order for these particles to follow these particles, apparently we need to get the leader's position, then use the position to set the follower's behavior. Let's look at how we can set this up. So go back to my Niagara system. First, we'll need to create a custom module, and we also need to decide where we want to put that module. Since the value that we are getting is position, and we want the followers to follow the leader, that means we need to be constantly updating the position value coming from the leader. So I'm going to put the custom module under the emitter update stage. By doing this, this module will be constantly run and we can constantly updating the position value. Alright, I'm going to click this add button. Then I'm going to type in scratchpad. First thing, I'm going to rename this local module. So go to this tab. I'm going to rename it to mms_getLeaderPosition. Alright, inside of the map get here, first I'm going to add a new value, and this value will be attribute reader. So you can see I have this particle attribute reader here. I'm going to select it, then I'm going to rename it to leading emitter. So this will be our leader, and later when we use this module, we need to fill in the emitter's name in order for this input to be valid. Alright, after that, I'm going to drag out this pin. Then I'm going to type in get position, and you can see we have two options in here. One is get position by ID, another is get position by index. We're going to talk about ID later. For now, I'm just going to use this get position by index. Alright, first thing, we need to fill in the name of the attribute. Well, here we are getting the position, so the name of the attribute would be position. Alright, and the next input we need to fill in is this particle index. So what does this mean? Well, let's take a look at this emitter for example. So this emitter is spawning 10 particles, and say now we are getting the position of these particles by using this node get position by index. So basically what this node is doing is we want the position of these particles, but we need to define which particle's position that we are getting. And we can use the index to help us to get the info. So in here we have 10 particles, so their particle index will be starting from 0 and end with 9. So this is the same as we use array in Blueprint. The index of the array will start with 0. Alright, let's look at how we can use this information to help us to get the position of the leader. So go back to my Niagara. Now that we know, we need to fill in the index, but apparently here we need to fill in some kind of random value. And also this random value needs to be a valid index in order for this position to be valid. So first, we can drag out a pin from this leading emitter, and we can type in get num particles. So same thing as operating inside of array, we first need to get hold of how many particles this emitter is currently spawning. Alright, I'm going to drag this out. Then I'm going to use another node, so it's called calculate random integer. And you can see it's right there. I'm going to bring it out. So for the integer min, a 0 is fine in here. So this means the first particle inside of this emitter. And for this integer max, well, this will be the non-particles minus 1. So I'm going to use the subtract node in here. And the value that I'm plugging into the socket B will be another integer. So inside of Niagara, we can right mouse button click and type in the value type that we want. So in this case, it will be int. And we can select this int32 in here and change this value from 0 to 1. Then plug this into socket B. Now this value here will be the total number of the particles minus 1. And plug this into integer max. And the random value coming from this pin will be a valid index. And we can use this value to get hold of the position of those particles we want. So I'm going to plug this into particle index. And just like that. And what this node will output is all the position values coming from the leader. And I'm going to output this value. So I'm going to drag these nodes out, and I'm going to connect this pin to here. And you can see a new variable has been created, and it's under the namespace local. So for the things we want, using a local value just won't work. So same as a local variable inside of a Niagara function, this value is only visible to this graph and this graph only. We cannot access this inside of our Niagara emitter. So apparently we need to change this namespace. So I'm going to right mouse button click and go down to change namespace. And you can see we have many options here. We have system, emitter, particles. Which one can we use in here? Well, to answer that question, we need to talk about these namespaces a little bit. More specifically, the accessibility of value under certain namespace. So let's start with system. For parameters that belong to system, so that means if one module inside of our emitter want to access this value, it's okay. If it's from the particles, it's doable as well. Note that a value must be set before it's read. So we need to use a module to set this value, then the module under it can access it and the module above can't. If we forget this rule, we'll just get a lot of error messages and sometimes even crash our editor. Alright, and for parameters inside of emitter namespace, they can only be read in emitter stage and particle stages. And for parameters inside of particles namespace, they can only be read in particle stage. And for parameters belong to output, so it can be read in stage further down. If we are setting a variable inside of a module under particle stage and we mark that variable as an output parameter, then that value can be read in modules or stages further down. And one important thing here is the value here, it does not persist between stages. So if we were setting this variable inside of emitter stage, then that value cannot be passed to particle stage, because this value just does not persist between stages. And we also have a transient namespace, and this rule here applies to transient parameter as well. And we have one more left, and that is this stack context. So for stack context parameters, it can be read in any modules, and it does persist between stages. So this is a very special one, keep that in mind. Alright, go back to my Niagara system. Now that we know all the meanings for those different namespaces, I'm gonna right mouse button click and change the namespace, and I'm going to change it to emitter. And that's because this emitter that we created, we put it under the emitter stage, and for parameter inside of emitter stage, it can be read inside of particle stages, and that's perfect. After I say it, I'm going to read this value inside of particle stages, and I'm going to rename this value to leader position. Alright, just like that. And I'm going to click apply scratch. Then go back to my system overview. Now if I click this module, you can see I'm getting some warning messages. And that's because it has one function input, particle attribute reader. So in here, we need to specify the name for the emitter. And in this case, will be leader. So I'm going to type in leader. And you can see it's right there. So I'm going to select it. And now you can see that warning message is gone. And if I click this view option, and click this show parameter rights inside of this dropdown, you can see we are writing this parameter inside of emitter stage, and this is the new value that we've just created. And I want to use this value under particle stage. More specifically, I'm going to go to this shape location, and for this shape origin, you can see it's using a stack context parameter. I'm going to change this to the parameter that we just created. So we can find it inside of our parameter map under emitter attributes. Scroll down, you can see I have this leader position in here. I'm going to drag this parameter out and place it in here. Now if I click play, you can see this is what I get. So we are constantly updating the shape origin of our shape location of these particles, and this is the effects that we get. Looking pretty cool. Now I'm going to drag this out to my level. So go back to my level, I'm going to drag out this Niagara system and lift it up a little bit. And you can see this is what we get. Here I'm just using some simple sprites, but this can be anything. You can change these followers into some smoke or some fire or even some matches. And the leaders here, you can change them to anything else you like as well. This is what we get. Looking pretty cool. So these are the two emitters that I just created. And for the modules inside of them, there's really nothing too fancy. And the key is this custom module that we just created. So these are all the nodes that I used. Feel free to use this as a reference if you need later when you are creating your own. And I'll see you in the next lecture. Welcome! In the last lecture, we created this follow the leader symbol VFX, and we also went through some of the basic concepts of those different namespaces and the accessibilities of the parameters under them. And before we move on, there's one cool thing that I want to show you. So for this Niagara system, for the follower, besides using a sprite renderer, we can also add in our ribbon renderer. So I'm going to right mouse button click to add an emitter. Then I'm going to go to Simple Sprite Burst. I hope you still remember how to use a ribbon renderer. So we need to delete this sprite renderer and use ribbon renderer in here. So first thing, I'm going to change its name to following ribbon. Then for this emitter state, I'm going to change it to infinite as well. And delete spawn burst instantaneous. Use the module spawn rate instead. So the default value would be 100. That's something Unreal uses. Then same as the follower, it needs to have the same custom module. If you recall, a scratch pad module will only be visible to the emitter where it is created. So in here, we cannot access this module, but we can just simply copy and paste the module to here. So I'm going to select this module, copy it, then paste it to here. And same as our follower, we need to give it the leader name. So it'll be leader. So select it, then go down to initialize particle. I'm going to change its lifetime to be 1 second. Change its color to something maybe yellowish and give it a value of 10 as well. Now we are still not seeing anything, and that's because there are 2 more things that we need to do. So first, we need to set this ribbon width. Instead of unset, I'm going to change it to direct set and change its value to something like 3. And in order to see the ribbon, we need to use the module shape location, and now you can see it's there. And same as our follower, for this shape origin, I like you to use the same value, so it'll be this leader position. So go back to this emitter, it'll be under emitter attributes. Then I'm going to drag out this parameter and place it in here. And after I do that, you can see I get an error message. And if you go to the Niagara log, you can see the variable emitter.leader position was red before being set. But I don't think this is true, because this parameter is being set inside of emitter update. And to quickly get rid of this, we can just adjust the order of this custom module inside of the call stack. So I'm going to move this above spawn rate, and now you can see the error message is gone. I think this is a bit too dramatic, so go to this shape location. For the sphere radius, instead of 100 units, I'm going to lower it down to something like 0.1. And you can see this is what I get. Maybe 1 for the sphere radius. And looking pretty cool. And go back to my level. By using the same custom module and a ribbon renderer, this is what we can get. Alright, now after the understanding of custom module and namespaces, we can create a more advanced version of this. So right now, this version, it works, it just looks a bit chaotic. What if I want a more deterministic one, a more stable one? How can I do that? So same as the one that we created. In order to have a more stable version of this, we'll need the leading emitter and the following emitter, and this following emitter needs to pull data from this leader. But after getting hold of the position data we want, there are some other things that we need to do. So basically, we need to use the target particle's position to subtract the follow particle's position, and with the new vector that we get, we can use it to set the follow particle's velocity. Since the position of the target particle is constantly changing, and if we use this new vector we get to set the follow particle's velocity, we can get a more stable version of follow the leader. Now you might be wondering, how does this work? Why do we need to use one vector to subtract the other? Well, to answer that question, we need to talk about vector math a little bit, and we're going to use some 2D vectors as example. So here you can see, inside of this 2D space, I have 2 points. The first one, let's say it has a coordinate of 5 in the x and value of 3 in the y. And this will be the vector. And the origin is here. And the position for the second dot, let's say it has a value of 3 in the x and a value of 1 in the y. And this is its vector. So now, this point here, this is our leader. I'm going to call it V1. And this here, this is our follower. I'm going to call it V2. And the things that I just show you is, I'm going to use V1 to subtract V2. What's the result that I'm going to get? Well, the math here is, we're going to use 5 to subtract 3, use 3 to subtract 1. And the new vector, V3, that we're going to get will have a value of 2 in the x and a value of 2 in the y. So, this is the new vector. How is this new vector going to help us to achieve what we get? Well, now if we move this vector to this spot and use these 3 vectors to form a triangle, this is what I get. So by using one vector to subtract the other, we can get a new vector that's pointing from the second vector to the first vector. So something like this. And with this vector, we have direction information, we have distance information. We can calculate how far away are these 2 points from one another. And this is something that we can use to directly set the follower's velocity. If you recall, for velocity, it needs direction information and speed information, and a vector can have both. So the important math here is, using one vector to subtract another, we can get a new vector that's pointing from the second vector to the first vector. Keep this in mind. And now let's examine what we've just learned. So we are still having these two same points and the same coordinates. But now, if I use v2 to subtract v1, what's the new vector that I'm gonna get? I'm gonna pause here for a few seconds, think about the answer. Welcome back. Hopefully you got the answer already. So the new vector that we're gonna get, let's do a simple math in here. So use 3 to subtract 5, we'll get -2. Use 1 to subtract 3, we'll get a -2 as well. So the new vector v3 will be something like this. So same as what we did before, let's use these 3 vectors to form a triangle. And now if we move this vector to here, this is what we get. You can see, comparing to our last v3, this one, it has the same length. So the distance between these 2 points are the same, but the direction information is the exact opposite. So we are getting a vector pointing from v1 to v2. Alright, that's the vector math that we need to know in order to create the effects that we want. Alright, go back to my project. I'm gonna duplicate this demo display again, and I'm gonna rename this to follow the leader advanced. And I'm gonna create a new Niagara system for it. So right mouse button click, create new Niagara system, select simple sprite burst, click add, click finish. I'm gonna rename this to ns_follow the leader advanced. And just to save us some time, I'm gonna steal some emitters from this one. So double click to open it, and double click to open this advanced one. I'm first gonna delete this default one. So I'm gonna copy the leader emitter from this one, and I'm going to paste it in here. Since I want a more stable version of this, I no longer want to use spawn rate. Instead, I'm going to use spawn burst instantaneous, and I'm going to change its spawn count from 1 to 5. Alright, something like this. And I'm also going to change its lifetime. So I'm going to click reset in here, and I'm also going to delete this scale color module. I don't need that. So this is what I get for my leader. Alright, I'm going to create my follower. So right mouse button click to add emitter. Then simple sprite burst, I'm going to rename this to follower, and for this one it only needs to be something simple. So emitter state, change it to infinite, and spawn burst instantaneous, I'm going to change its spawn count to be 30. Inside of initialize particle, I'm going to change its color a little bit to something pinkish, and click OK. Bright size mode, lower it down to 10. And next thing, we need to create some custom modules for this follower. Like I mentioned before, there are 2 ways to create custom Niagara modules. Besides doing it inside of this emitter directly, we can also do it inside of our content browser. So we can right mouse button click and go to FX and scroll down. You can see there's this Niagara module script. So I'm going to select it, and to achieve the behavior we want, I'll need 2 custom modules. So for the first one, I'm going to rename it to mms_get leader ID, and double click to open it. So a custom Niagara module created this way, we'll need to set some of the properties in here in order for it to be visible to our emitter in our project. So first thing, I'm going to set its category. Instead of default, I'm going to change it to custom. Then scroll down. For this library visibility, currently it's set to be unexposed. So later, if we don't change this, when we search for this custom module, we won't be able to see it. So I'm going to change this to exposed. Now it's visible to our emitter. Then we can also set the description text, the keywords in here. So this is like the comment for a Niagara's module. You can write in something in here if you want. And for the keywords here, this is something that can help us to search. So I'm simply gonna name it get leader ID. Alright, same as the last one that we created for this function input. First, I'm gonna type in attributes reader, and I'm gonna change its name to leading emitter. So what this module needs to do is, it needs to get the ID from the leader. And the node we need is called getID at spawn index. And now you might be wondering, why do we need to get ID this time? So let's use these 10 particles as an example again. The reason why I need to get hold of the particle's ID is, later for getting their position, I'm going to use the node getPosition by ID. So comparing to getPosition by index, the particle ID, unlike index, it's persistent. So no matter how many particles this emitter spawns, all the particles will have a unique ID. And that's something that we can use to help us to achieve what we want. So go back to my Niagara system. For this spawn index, well, we can do something similar as what we did before. So we can first use the node get non-particles, then subtract 1, bring out an int32, change the value to 1, and plug this into socket B. Then I'm going to use the module calculate random integer, and we can use this to help us to get a random index, and plug this into integer max and plug the random value into spawn index. And now we have the ID we need. Then I'm going to output this ID, so plug this pin to here, and I'm going to change its name to leader ID. And the local here won't work, so we need to change the namespace. Right mouse button click and change its namespace. So now we need to think about which stage we want to put this custom module. Well, in this case, I'm going to put it under the particle stage. So each of the particle will get the leader ID when it's spawned. Then it will use that ID to update its velocity during particle update. So all the things that we need to do are inside of particle stage. So the namespace particles will work in here. I'm going to select it. Then I'm going to go to here and click apply. And go back to this follow the leader advanced. So under the particle spawn stage, click add button and type in MMS. And you can see this is the module that I just created. If you are not seeing this later, make sure you have ticked expose to library and click compile. Alright, I'm going to click this module. Then here I'm going to type in the name leader. Then go to here, click show parameter rights, and you can see it's writing to this parameter leader ID. Alright, this is something that we can use further down the stage inside of particle update stage. And for that, we'll need to create a new custom module. So I'm going to go back to my content browser, right mouse button click, go to FX, Niagara module script. I'm going to rename this to MMS underscore update follower velocity, and double click to open it. So first thing, change its category to custom, expose to library, keywords here, type in update follower velocity. And in here, we need to create a few inputs. So first, we'll need an attributes reader, and this will be leading emitter. Alright, then I'm going to drag out this pin and use the node get position by ID and change this attribute to position. And in here, we need to fill in particle ID, and that will be another function input. So later, when we use this, we can use the parameter we set in the last module that we created. So click add in here, and I'm going to type in ID. And select Niagara ID. I'm going to rename this to in leader ID. Alright, connect this to particle ID. And now, the value here will be our target location. And before we perform some math in here, I'm going to create another function input. So this will be a vector. And I'm going to call this target position offset. The reason why we need this is, if we don't set this, all the followers will be overlapping with the leader. In order to separate them, we need to give them a bit of offset for their target position. Alright, I'm going to drag out this pin and use add. And add this target position offset. So this will be our new target location. I'm going to comment this quickly and type in target location. Alright, after getting hold of this, let's do a bit of vector math. So drag out these two nodes. If you recall, we need to use the target location to subtract the follower's location. And for that, we'll need to create another value. And this one, it doesn't need to be an input. It'll need to be one of the core parameters. More specifically, it'll be the particle's dot position. So this will be the follower's position. And I'm going to use a subtract node. And plug this into socket B. Alright, now we are getting a vector pointing from follower to leader. And by using this vector, we can achieve what we want. So I'm going to drag out these two nodes again. And drag out this pin. So I'm going to break this vector by getting its direction and its length. And there's a node just for that. It's called direction and length safe. And you can see here it outputs two pieces of information, the direction of the vector and the length of the vector. And we can perform a little bit of math in here to combine these two as velocity. So the length here, this is the distance. And in order to get the correct speed, we will need to create a new value in here. So this value, it will be delta time. And you can see this value is from the namespace engine. So I'm going to bring it out. Now I'm going to divide this length by delta time. Connect this to socket B. And drag this pin down a little bit. So now what we are getting here is use distance divided by delta time as the correct speed. Increase this comment box a little bit. And now we have the speed, we have the direction information, we have our velocity. So last thing, I'm going to use a multiply node. So drag out this pin, type in multiply, plug this into socket B. And in here, create a new parameter. It will be from the core parameters, and it will be particles.velocity. Plug this into here, and that's it. I'm going to click apply and go back to my Niagara system. Under the particle stage, I'm going to bring in that module that I just created. So it will be NMS, update follower velocity, and emitter name here, fill in leader. And you can see here, I'm getting some errors. And here it says source emitter needs persistent ID set. So hope you remember this. Back in the last section, when we are using the location event, we take the properties requires persistent ID. And this is why. Because we are accessing this ID, so this emitter, all the particles, they need to have the persistent ID. And in order to do that, we'll need to take this. Alright, I'm going to take it and go back to my update follower velocity. You can see that warning message is gone. And there's one more function input that we need to fill in. So it will be this in leader ID. And for that, I'm going to go to particles attributes and drag this variable to here. Alright, now if we zoom in, so those particles, they're actually following these leaders. And the reason why we cannot see them is they're overlapping with these leaders. And in order to give them some position offset, we can set it in here. So I'm going to change this to a random vector and increase this vector scale to something like 50. And you can see this is what I get. I'm going to delete this scale color module. Then I'm going to drag out this Niagara system. So drag it out and place it above this demo display. And you can see this is what I get. I have a more stable behavior. And the reason why there's a bit of jittering is when the leader dies and reborn, we are resetting this follower's position. And if you think this is annoying, you can increase their loop duration. So instead of 2, you can try 5. Change this to 5 as well. And since we changed the loop duration, we need to change its lifetime as well. So set this to 5 and set this to 5. So this will help this situation a little bit. And you can see this is what I get. Looking pretty cool. So these are the two emitters that I just created. And with a bit of vector math, we can create something much more interesting. And for the two Niagara modules that I just created, you can download them in the resources dropdown of this lecture. So if you get stuck later, you can check out all the nodes that I use inside. Alright, it's time to create your own, and I'll see you in the next lecture. Welcome. Starting from this lecture, we'll look at how we can create a rain effects like this. So how can this be achieved? So this is a VFX that combines material effects and particle effects. And once I break it down to you, you'll find that it's actually not difficult to do. But before we dive into our project and start to create this, there's one knowledge gap that we need to fill, and that is the Fresnel effect. So for creating the rain effects, apparently we'll need a lot of raindrops That means we'll create some liquid materials. And to create the liquid materials, in order for it to look better, we'll need to use the known Fresnel. So this is the Fresnel effect, and it's also known as the rim lightening. So you can see the color of the edge of this object is different from the color in the center. So by using the Fresnel node, we can simulate an effect like this. So let's look at how we can visualize this in Unreal. Go back to my project. I'm going to create a new room inside of this BP demo room. So I'm going to select it. Then first I'm going to assign my first room a name. So I'm going to call this room Custom Module 101. Then I'm going to decrease its length from 5 to 3. Since we only have 3 BP demo displays inside of this room. Then I'm going to create a new room. So we can click this button to create a new one. And you can see I have a second room, and this is the room name for my first room. I'm going to go to my second room, and for this one, I'm going to adjust its height. So we can click this index 1. This is my second room. And for the room name, I'm going to name it Rain Effects. Then I'm going to lower its height down to 7. Then decrease its length from 5 to 3. Alright, this is the room later we're going to put the VFX in. Then I'm going to duplicate another demo display. And I'm going to change its name to Fresnel Example. And next thing, I'm going to create an example material for it. So go back to my Niagara folder. Inside of examples, create a new folder. I'm going to call this one Fresnel Example. And double click to open it. Create a new material. Name this m_Fresnel Example. And double click to open this one. And first thing, for the shading model, I'm going to change this from default lit to unlit so that we can better visualize the node. And I'm going to right mouse button click to bring out the node. So it's called Fresnel. And you can see in here we have two options. The one under utility, this is the most basic one, and this Fresnel function. This is a much more advanced one, and it gives us more control over the Fresnel effect. And we only need to use this one. So I'm going to use the first one. And you can see for this node we have 3 function inputs: exponent in, base reflect, fraction in, and this normal. And we're going to start with the input socket normal. Since the value that we plug into the normal socket will affect the Fresnel effect greatly. And you can see here it says defaults to pixel world normal if not specified. What does this mean? To answer that question, let's talk about surface normals a little bit. So there are 3 types of surface normals. The first one, this is known as the face normal. So you can see I have these red lines pointing straight out from each of the face, and that's what normal is. So with normals, it can tell us the facing direction of this face. And with the direction information it can provide, we can perform more math operation based on it. So this is the face normal. And the second one, we have the vertex normal. Unlike the face normal, where the normals are pointing straight out from the face. Inside the vertex normal, these normals are pointing straight out from the vertices on this object. And same as the face normal, it can provide us with the direction information of each of the vertices. And the last one, we have the pixel normal. And this is the normal for the pixel that's being rendered on our screen. Technically speaking, a pixel shouldn't have any directional information. So when talking about pixel normal, we always need a normal map for this to work. And if you recall, back in the Fresnel node, the input for the normal socket defaults to pixel normal workspace. So if we don't have a normal map specified for pixel normal, the pixel normal workspace is very similar as vertex normal in here. Alright, now that we understand the different normals, and we can use those to help us to understand the Fresnel calculation. So how is this rim lightening achieved for Fresnel effect? So basically, it takes 2 factors into account: the surface normal of this object and the facing vector of our camera. So when the surface normal is pointing straight at the camera, we'll get no Fresnel effect. So you can see in here, we get a value of 0. So basically, these 2 vectors, they have the exact opposite direction. And when the surface normal is perpendicular to the camera, we get the full Fresnel effect. The surface normal here will be pointing to this direction, and that is perpendicular to our camera vector. And in this way, we'll get a value of 1. So, full Fresnel effect. And with that out of the way, I'm going to first plug this into emissive color directly. And you can see this is what I get. When the surface normal is pointing straight at the camera, I get a value of 0. And when the surface normal is perpendicular to our camera, I get a value of 1. Alright, I'm gonna first bring in this material to our level. I'm gonna click apply in here, then go back to my level. I'm gonna create a material instance from it. Then I'm gonna fix its naming convention. So I'll go to here, click this button, and I'm gonna untick this change main name and click OK. Alright, I'm gonna drag out a sphere. Go to place actors, inside the shape, drag out a sphere and increase its size a little bit to something like this. Then I'm gonna assign it this material instance. So inside of the details panel, click this button, and you can see this is what we get. Depending on the position of our camera, this is the effect for the node. Alright, I'm going to go back to this material, and we still have two function inputs. So the first one, this is the exponent in. So hold down S on my keyboard. Since we don't know what this value will be controlling, I'm simply going to name it for now exponent. And I'm going to give it a default value of 3 and plug this into here. Then click apply, go back to my level, open my material instance. So let's try to adjust this value and see what we can get. So I'm going to take this. Then I'm going to first lower down the value to 1. And you can see this is what I get. After I increase the value to 5, this is what I get. So the higher this value is, the further we will be pushing the Fresnel effect to the edge. If I have a value of 0.1, we only have a little Fresnel effect at the center. And if I have a value of 5, we can push the effect to the edge. So this is what this value is controlling. Alright, go back to my material. And the second input is this base reflect fraction. So what this value will affect is the fraction of specular reflection. Usually the default value here will work. But setting the value here to a number of 1, we can disable our Fresnel effect. So if I plug this value into this socket, you can see I get no Fresnel effect at all. I'm going to disconnect this pin. So we don't need to do much for this socket. And a more general use case of this node is we can use Fresnel as the mask and we give different colors to our object. So I'm going to change my shading model back to default lit. So I'll have access to the base color socket. And for the base color, I'm going to give it a different color. So convert this to parameter and call it base color. Give it a default color of something maybe greenish. And I'm going to plug this into my base color socket. Then for my Fresnel effect, I'm going to give it a different color. So I'm going to first delete this node, then duplicate this node. I'm going to change its name to Fresnel color and change its color to maybe something reddish. Then use a multiply node to combine these two together and plug this into emissive color. And you can see this is what I get. I'm going to click apply and go back to my material instance. So because the output of our Fresnel is a value between 0 and 1, and we can use that value as a mask to apply different colors to our object. Since a value of 0 will be output at the center, we get our base color, and the value of 1 will be output for the edge, we get our Fresnel color. And if we change this exponent value, say lower it down to 3, we get more red. Lower it down to 1, we get a lot more. Increase it to 6, we get less of the red. And it's time for a challenge. So a challenge is, same as I did, I'd like you to create an example material for the Fresnel node. One is for the base color of the object, another is the Fresnel color of the object. Then tweak the values inside the material instance to help you to better understand this node. And most importantly, get more comfortable with using it. There's something that we need to use for our rain effects. Alright, pause the video now and give this a go. Welcome back. Hopefully at this point you're already comfortable with the Fresnel node, and now let's look at how we can take this further. So I've just moved my demo display to the other side of the wall. You can do that if you want. I'm gonna go back to my material, and for this node we still have one more input socket to cover, and that is this normal. So you can see here it says defaults to pixel normal if not specified. Or if we give this input socket a normal map, what will happen? Well, let's find out. And for that, I'm going to create another material. So I'm going to duplicate our m_Fresnel example, and I'm going to rename this to Fresnel normal map example. Then I'm going to create a material instance after it. Fix its naming convention. Untick this change main name. Click OK. And double click to open this one. So for this one, I'm going to give it a normal map, and we can get one by go to our textures folder, and inside of this realistic VFX textures, if you scroll down, you can see there's this normal map. I think it will work great for our need. So it's called T_noise normal_A. I'm going to drag this normal map to this material, and I'm going to first disconnect this pin and move these nodes down. We don't need them for now. And I'm going to plug this into the normal socket and use that to drive the result of the Fresnel effect. So I'm going to duplicate this normal map. And very important here, before we plug this into here, make sure you use a transform vector node. Transform this normal from tangent space to workspace. If we don't do this, we might not get the result we want. So plug this into the normal socket. Alright, then I'm going to plug this back to our emissive color. So move these nodes up, then place them in here. Then I'm going to plug this into emissive color. And you can see this is the result I get. I'm going to click apply and go back to my level. I'm going to duplicate this sphere so we can compare the results of these two and assign it this material. And you can see this is the Fresnel effect using a custom normal map, and this is the Fresnel effect using pixel normal. So with the normal map specified, we get a much more interesting look, and we can get the Fresnel effect depending on the direction information our normal map can provide. And there are tons of things that we can do with this app. So for example, we can offer these spots some dark shadows, we can tint their color a little bit, and they're all commonly used techniques for objects in our scene. And there's one last node that I like to add to this material, so double click to open it. So before we plug the result into the emissive color here, very often we want to use another scalar parameter to control the strength of the Fresnel effect. So I'm going to call this parameter Fresnel strength and give it a default value of 1. And plug this into a socket, plug this into emissive color, organize my graph a little bit, drag this node down. And I'm going to click apply. Now go back to my Fresnel normal map example. I'm going to try to adjust the Fresnel strength. So instead of a value of 1, I'm going to change it to 3. And you can see this is what we get. If I change it to 10, we get a more dramatic look. I'm going to lower it back to something like 2. And this effect is entirely depending on the direction of these normals. And you can see for the spots that have this effect, the normals there are perpendicular to our camera. Keep that in mind. And this is something that we're going to use later for our rain effects. So these are my final notes for that example material. I highly recommend you to create one yourself. Use that to compare with the previous one we created. And now with this out of the way, in the next lecture, we'll look at how we can create our main raindrops. I'll see you in the next lecture. Welcome! In the last lecture, we created ourselves these two Fresnel examples, and in this lecture, let's look at how we can use what we've learned to create main raindrops. So for this raindrop, or for any liquid, usually the first thing we need is some normal map. And the reason why normal map is important, so if this is some water material, we'll need to use normal map to help us to simulate the waves, and also we'll need to have a mask. So for any liquids, apparently they are transparent objects, and in order to drive the transparency for the object that uses this material later, we'll need a texture to plug into the opacity socket, and more than that, we'll need to have refraction. So this is something that we've already used back in the section where we created the flamethrower. If you recall, after we apply reflection to it, we use a mask texture to help us to hide the seam, and we need to be doing the same thing in here. And for the liquid, apparently it needs some refraction as well. So we need to use this mask to hide the seam in here as well. Alright, let's look at how we can set this up. So go back to my project. I'm going to first go back to my Niagara folder. Inside of this custom module, I'm going to create another folder. I'm going to call this Rain Effects and double click to open it. First, let's get hold of the textures, and we can find all the textures we need under the realistic VFX textures. And you can see there are two textures. The first one is called this t underscore droplets underscore a underscore n. So this is the normal map. And this underscore a1, this is the mask texture. And I'm going to copy them to my rain effects folder. Select copy here. And I'm going to change their name a little bit. So for this one, I'm going to call it t underscore raindrop underscore normal. And for this one, I'm going to rename it to t underscore raindrop underscore mask. And the next thing, I'm going to create a master material for our liquid. And later, if we need to have more liquid elements, they can all be using the same master material. So I'm going to place that material inside of the material folder, right mouse button click, select material. I'm going to call this m underscore liquid master underscore diaparam. So later inside of this material, I'm going to use dynamic parameters to drive the data so that every raindrop will have a random value. Double click to open this. First thing, I'm going to change this blend mode from opaque to translucent. Change this from default lit to unlit. And I'm going to bring in those two textures. So go back to my rain effects folder, drag in these two textures, place them in here. Alright, move this node up, move this node down. And I'm going to convert them into parameters. So the first one, this will be the liquid normal map, and convert this into parameter as well. This one will be liquid mask. And I'm also going to bring out the dynamic parameter and keep everything at default inside. I will change the names for these parameters later. Alright, first thing, I'm going to bring out the particle color node. So I like to take care of the opacity socket first. And first, I'm going to bring out a multiply node. So the value inside of socket B, this would need to be our liquid mask. But if you take a look at this texture, unlike all the masks that we've used so far, it has some weird color. And when this happens, this means this is a channel packed texture. If you are from my material course, channel packing should be no problem for you. And in case you aren't, so basically, I'm going to click the magnifying glass to go to where the texture is located, double click to open it. For each of these different channels, they contain a different value. So I'm going to isolate the red channel first. This is what I get. And I'm going to isolate the green channel. You can see a completely different pattern. For the blue channel, this is its pattern. So for this texture, the mask that I'm going to use is stored inside of the green channel. I like to use this as the value that I plug into the opacity socket. So go back to my liquid master. I'm going to start caching the values that I need to use. So move these three nodes out and drag out this green channel, use a name rerun node. I'm going to call this cached liquid mask. Then I'm going to use that cached node in here. So plug this value into socket B, plug it into opacity, and change the preview mesh to plan. And this is what I get. And before I forget, I'm going to put this liquid mask into its own group. So I'm going to change the group to liquid settings and change its sort priority to be 2. Alright, the next thing that I want to solve is the emissive color socket. So bring out another multiply node, plug this into socket B. And the value inside of socket A here, all those VFX that we created so far, usually this is combined with some sort of texture. But since we're creating liquid here, the value I'm going to plug into here will be something different. I'm going to use a Fresnel node in here, and I'm going to use this value here to drive the color data of our raindrops. So the first input socket, this Fresnel exponent, I like to control it through our dynamic parameters. And later, inside of our Niagara system, we can give all of the raindrops a random value for this exponent. So for the first parameter, I'm going to change its name to Fresnel exponent and give it a default value of 5, and I'm going to cache this value. So use a name rerun node. I'm going to call it cached Fresnel exponent. Then use the name rerun node in here. So plug this into the exponent socket and keep the second value a default. So for the normal here, I'm going to plug in this value, and I like to cache it as well. So drag out this RGB pin, use the name rerun node. I'm going to call it cached liquid normal output. Then use that name rerun node in here. So bring the node out. Remember, here we need to transform our vector. So drag out this pin, use the transform vector node, and plug this into the normal socket. Alright, I'm going to move these 3 nodes out a little bit and move these nodes up. And before I plug this into socket A, I'm going to use another multiply node. So plug this into socket B. And for the A socket here, So this will be the value that's controlling the strength of this Fresnel effect. And for that, I'm going to use dynamic parameter to control it. So for the second parameter, I'm going to call it Fresnel strength. And use the name rerun now again. Call this cached Fresnel strength. And go back to here. Use the name rerun now. Plug it into socket A. And finally, we can plug this into here and plug this into emissive color. And you can see this is the result I get. So I'm going to quickly comment these notes. So what we are doing here is use Fresnel as mask to influence the color of particles. Alright, the next thing that I'm going to take care of is the refraction. So first, and for my raindrops here, I like each one of them to have a different refraction rate. And for that, we can use our dynamic parameter again. So for the third parameter, change its name to refraction rate. And I'm going to give it a default value of 1.33 and cache this value. So use the name rerun now. I'm going to call this cached refraction rate and use the name rerun now in here. I'm first going to plug in the value directly. So plug it in here. And you can see this is the result I get. Well, I need to find a way to hide this edge first. But for now, I want to see the result of this refraction. That means we need to plug something into the normal socket. Well, that can simply be the cached liquid normal output. So plug this into the normal socket. And you can see this is the result I get. And this is not working correctly. So now all my raindrops, they have the refraction. And that really isn't too ideal. That's not how raindrops should behave. And for that, there's another value inside of this liquid mask texture that we can use. So if I go back to it and I isolate the red channel, and this is a mask that's designed specifically for the refraction. You can see it has white values on the edge of these raindrops and black values at the center. And by using this as our mask, we can get the correct result we want. Alright, go back to my master material. I'm going to cache the value inside of the red channel. So drag this pin out, use the name rerun now. I'm going to call this cached refraction mask. And I'm going to go to here and use the mask. So we can use a lerp now. And for the value inside of socket A, I'm going to give it a default value of 1. I'm going to plug into this cached refraction rate. And the value inside of alpha socket, this can be our refraction mask. So plug this into here. And if you're wondering, how does this work? Well, the reason why this needs to be a value of 1 is I'm going to hold down 1 on my keyboard to bring out a constant, change this value to 1, and I'm going to plug this into the refraction socket. So you can see by doing that, we have absolutely no refraction at all. And that's the purpose of using the lerp now. Because we're plugging the mask into the alpha socket, for the white parts here, they'll have some kind of refraction, and for the black parts, they won't. And we can use this way to hide the edge as well. So, one stone, two birds. Go back to my master material. I'm going to delete this now, and plug this into the refraction socket, and organize my graph. And this is what I get, raindrops with the refraction ready. Looking pretty cool. I'm going to click apply in here, and the next thing we need to do is we need to use this material inside the file Niagara system and use that to simulate the raindrops. We'll look at how we can do that in the next lecture. Alright, let's do a little bit of recap. So for my liquid master, I first catch all of the values coming out of these textures. For this liquid mask inside of the red channel, this is its refraction mask. The green channel, this is mask that we can plug into the opacity socket. And I also use the dynamic parameter to drive all the data so that later we can use dynamic inputs to provide these particles random values. And then using all of the cached values, I first set up the Fresnel mask and use that to influence the color data coming from the particle node and use the liquid mask to plug into the opacity socket. And the next thing is our refraction. So by plugging into a value of 1 into the refraction socket, we won't have any light bending. So by using a lerp node in here, not only can we get the correct result, we can also use this to hide the seam of our texture. And of course, in order for this refraction to work, we'll need to plug something into the normal socket. And that's pretty much it. Alright, and it's time to create your own liquid master. Refer back to the video if you need help. And I'll see you in the next lecture. Welcome! In the last lecture, we created this master material for our liquid. And in this lecture, let's look at how we can use this to create the main raindrops. So first, I'm going to go back to my project, and I'm going to create a material instance from this. Then fix its naming convention. I want to change main name this time, so I'm going to name it main raindrops and click OK. Alright, I'm going to drag this material instance to my rain effects folder. So drag inside, select move here, and inside of it, I'm going to create a Niagara system. Select next, and I'm going to use simple swipe burst to begin with. Click finish, name this to NS rain effects, and double click to open it. So first thing, I'm going to rename this emitter to main raindrops. Then I'm going to assign it that material instance. So select it, click this button, and I'm going to click pause in here. So you can see this is what you get. And apparently, this is a flickbook texture. First thing, let's get this size correct. So for this sub image size, it's 3 elements on the X and 2 on the Y. Alright, that's it. And I'm going to give it the module sub UV animation. Change this renderer to sprite renderer and click play in here. And you can see this is what we get. Alright, I'm going to start from top. So go to emitter state. I'm going to change its loop behavior from once to infinite. Then delete spawn burst instantaneous, use spawn rate instead. And for its spawn rate, I'm going to use a number of 5000 to begin with. Because later we'll need to send collision events using this emitter, we cannot set the property here to be GPU sprites. Keep that in mind. Alright, next thing, go down to initialize particle. For its lifetime, I'm going to give it a random value. So somewhere between 0.5 and 1.5. And for the sprite size mode, you can see right now, these raindrops, they are kind of too round. I like to stretch them a little bit so that they'll look like the raindrops. And to do that, for this sprite size mode, we need to change this to non-uniform. And I'm going to go with this random non-uniform. So for the sprite size min, I think I'm going to start with a value of 0.5. Sprite size max for the X, a value of 1 is fine here. Alright, sprite size min for the Y, I think I'm going to go with a value of 15. And sprite size max, give it a default value of 100. Now you can see this is what we get. Alright, next thing, I'm going to break their spawn location. So use the module shape location, and we have a lot of raindrops, and I'm going to change this to box plane and change the box plane mode to plane. For the plane size, I'm going to promote this to a user parameter, so that later when we drag this Niagara system to our level, we can directly adjust the size in here. So type in user parameter and select this re from new user parameter. And I'm going to add one more module to it. Then I'm going to start to adjust this in the level. So the next module, I'm going to add in gravity force. And now these raindrops, they will fall. Alright, I'm going to drag this into my level. So go back to my level. I'm going to first drag out this Niagara system and lift it up a little bit and move it to something like here. Alright, then I'm going to increase this plane size. So for the X, I'm going to try a value of 2000 first. For the Y, a value of 1000. And now, this is what we get. Now we have some raindrops in our level, and apparently we need to keep adjusting properties. So bring in my Niagara system, and I'm going to adjust the size of this window to something like this, so that I can see these raindrops. And next module that I'm going to add in, so I'm going to use scale sprite size. And after some experimentation, I found out that a curve like this works the best, and I think this is how a raindrop should behave. Its size should increase as it ages. Alright, this is what I have. And the last module that I'm going to add will be the dynamic parameters. So there are quite a lot of properties inside that we need to tweak. The first one, for this Fresnel exponent, I'm going to change this to a random range float. So I'm going to use a value between 3 and 5 to begin with. Then it's this Fresnel strength. For this one, I'm going to give it a random range flow as well. So somewhere between 3 and 5 would do, I think. And now you can see this is what you get. Alright, and the last thing, this refraction rate. So I'm going to give this a random value. Somewhere between 1.2 and 1.33, I think. We can also come back to change this later. And there you go. We have our main raindrops ready. Currently, I think it's not making a lot of sense because it's sunny days outside and we are raining inside. To quickly adjust that, we can go back to our outliner. In order to get a cloudy sky, the things that we need to adjust is this sky atmosphere. So select it And if you scroll down, there's this main scattering scale. So this is the key factor in order for us to have a cloudy sky. And the value of this depends on the brightness of our main light source in the level. So the higher the brightness, the higher this value needs to be. And usually it needs to be a value above 1. So I'm going to start increase this value. And you can see I'm getting the cloudy sky I want. Something like that, I think this will do. And now our raindrops are looking much better. And currently, if you think they are not obvious enough, we can go back to our Niagara system, go inside of initialize particle, and in here, we can change the value of the color. So currently it's 1. If I change this to 3, you can see they're a lot brighter. I think this is way too bright, so maybe a value of 1.2. And click OK. Yeah, something like that. And if you think this is spawning too many, we can adjust its spawn rate. If this is not enough, we can increase this spawn rate. So I'm going to make this a user parameter as well. And go back to my level. Press G to show my Niagara system. Scroll up. Press G again. So I think I'm going to lower it down to something like 4000. Alright, something like that. Looking pretty cool. So this is the emitter that I just created. Once we have the material done, there isn't really too much that we need to do inside of here. And these are the values that I use for my dynamic parameter. Use this as a reference, but don't hold on to it. For an environment effects like this, it takes quite some tweaking to make things look right. So I might come back to adjust these values later. Alright, time to create your own main raindrops, and I'll see you in the next lecture. Welcome! In the last lecture, we created these main raindrops, and before we move on, I like to tweak its properties a little bit. So double-click to open this NS Rain VFX. So I'm going to tweak the value inside of the color here in order to make it more obvious. And more than that, I'm going to change this into a random value. So I'm going to select this random range and copy this color, paste it to here. And for the minimum brightness, I'm going to give it a default value of 0.9. So they'll be a bit darker. And for the maximum color, I'm going to give it a default value of 1.5. So a bit brighter. Then go back to my level. And you can see this is what I get. So maybe 0.9 is too much. I'm going to change this to 1.2 and increase the maximum to 1.8. And this is what I get. Alright, something like that. Just a little extra variation for our raindrop. And in this lecture, let's look at how we can create the rain splash for these effects. Same as any other VFX, we'll need to find ourselves some textures. And just to remind you, our master material for liquid, it needs 2 textures. So it needs a mask, it needs a normal map. So let's get hold of this mask first. I'm going to go back to textures folder inside of realistic VFX. If you scroll down, you can see there's this texture T_splash_8 and double click to open it. And this can be our mask. So I'm going to copy this texture to my own folder, drag it to Rain Effects, select copy here. Then go to my materials folder, create another material instance, fix its naming convention. So this time I want to change its main name. I'm going to change it to Rain Splash and click OK. And I'm going to move this material instance to my Rain Effects folder. Then inside of it, I'm going to swap out the texture. So take this liquid mask and fill this texture in. Alright, that's one texture taken care of. And we still need to swap out this normal map. But sadly, we don't have a normal map for it. So under the realistic VFX textures, unlike the droplets in here, for the splash texture, there isn't a specific normal map for it. But don't worry, we have a replacement for the normal map. So you can see this T_noise normal. This one is perfect. For this normal map, it has many details, and we can use this as the normal map for our splash texture. So I'm going to copy this one to my own folder as well. So drag it to here, select copy here, and go back to it, fill it in. So open this material instance, select this normal map, fill it in. And now we have an issue. So you can see, after we start to use this texture, we are getting this seam. And the reason for that is, I'm going to go back to my liquid master material, double click to open it. So how we're hiding the seam relies on the mask in here. And if we go back to this texture parameter, we are caching the value stored in the red channel as the refraction mask and green channel as the liquid mask. But for our splash texture, this is not a channel pack texture. And if we use the same setup, it's just not going to work. So this is its value in green, this is its value in red. The pattern inside cannot be used as a mask. So its mask is stored inside of the alpha channel, and this is something we can use. So we need to modify our master material a bit. Alright, go back to my master material. I'm going to drag out this alpha pin and use a name rerun node. I'm going to call this cached alpha mask. And for this name rerun node, I'm going to change its name a little bit. So instead of liquid mask, I'm going to change it to green channel mask. And while I'm at, I'm going to put this texture parameter into its group. So liquid settings, give it a sort priority of 1. Then we need to use different static switches to help us to switch between these two masks. So I'm going to first create a bool parameter, and I'm going to call this is mask stored in alpha. And right away, I'm going to cache this value. So drag it out, use the name rerun now. I'm going to call this cached is mask stored in alpha. Then I'm going to go back to where we are first using the mask. So it'll be here. So I'm going to move these nodes out a little bit, just to give me a little bit more space. And in here, I'm going to bring out a static switch. And the value here, I'm going to plug in cached is mask stored in alpha. So when this is true, our cached node, cached alpha mask, will go through to the final output. And when this is false, this cached green channel mask will go through and plug this into B socket. Alright, this is the first modification that we need to make. And the second one, this refraction mask, we need to use the same setup. Otherwise, we'll have a visible seam for our texture. So I'm going to copy this node and copy this node. Press Ctrl plus D to duplicate them. And I'm going to copy this one as well. Press Ctrl plus D. So when the value is true in here, our alpha mask will go through. When it's false, this refraction mask will go through and plug this into alpha socket. Alright, that's another modification that we need to make. And before I forget, I'm going to put this parameter into the group liquid settings, change its sort priority to be 3. And I'm going to start to organize my graph a bit. Alright, something like that. Then I'm going to click apply and go back to my material instance, ren splash small. Then in here, I'm going to take this bool parameter, and you can see this is what I get. Currently, the color of these patterns is black. Don't worry, we still need to make some changes inside of dynamic parameter, since this is caused by our refraction amount. Hey, this is me from the future. So actually, this is not caused by refraction amount, but the strength of our Fresnel effect. So later, when we bump up this value inside of our dynamic parameter, we should be able to get rid of this issue. Alright, back with the old me. And it's time for a challenge. So a challenge is, I'd like you to modify the liquid master material for the splash texture, because if the mask in there is stored differently, we need to handle it differently. And after that, same as I did, I'd like you to assign the textures to the material instance. Alright, pause the video now and give this a go, or refer back to the video if you need help. Welcome back. Now let's look at how we can use this material instance inside of our Niagara system. So go back to my NSRAM VFX. In here, I'm going to create another emitter. And scroll down, select Simple Sprite Burst. I'm going to change its name to Ren Splash Small. And I'm going to isolate this emitter first in order for us to better see it. So first thing, change its loop behavior to be infinite. Then go to Sprite Renderer. I'm going to assign it that texture. I'm going to assign it the material instance. So it'll be mi underscore ren splash and select it. And this is what we get. So this is another for liquid texture. Let's get the sub-image size correct first. So it'll be 4 elements on the X. And right now it's a bit stretched. So we need to tweak its size. Go to this initialize particle. I'm going to change this sprite size mode to non-uniform first. Then I'm going to multiply this vector by a float. And later, if we want some randomness, we can just use this float. So for the value of x, I'm going to first try 50, and the value of y, I'm going to first try 100. And you can see this is what I get. Looks a bit more normal now. I'm going to come back to adjust this later. And next thing, I'm going to give it the module sub UV animation. Assign the sprite renderer in here and click play. So you can see this is what I get. Then I'm going to add in the module dynamic parameter and start to adjust the values here. So for the Fresnel exponent, give it a render value somewhere between 3 and 4, I think. And for Fresnel strength, I'm going to give it a render value as well. So somewhere between 0.8 and 1.5. I'm going to pause in here. So the strength is not high enough. Maybe a value of 1.5 and 2. Or maybe 2 and 3. Alright, something like that. Very close now. So 2.5 and 4 maybe. We can always come back to adjust this later. Alright, and this refraction rate, give it a render value. So somewhere between 1.1 and 1.33. And since this is rain splash, its lifetime shouldn't be too long. So next thing, I'm going to go to this initialize particle, change its lifetime to a random value, somewhere between 0.3 and 0.5. Alright, and it's time to actually spawn this rain splash in our VFX. So I'm going to cancel this isolation and go back to my level. So let's think about that. When do we want to show those splashes? Well, it'll be when these raindrops hit the ground. But when does that happen? Well, we can use a module, collision, to decide. So go back to this Niagara system. If I add in the module collision in here, we should be able to know when these raindrops collide with our surface. But with this app, we should have one issue. Let me just quickly show you what that is. So I'm going to increase its lifetime for these main raindrops. That's for testing. Increase it to something like 2 and 3. And go back to my level. Now you can see, this is the issue that I'm talking about. Since we enabled the collision module, these raindrops are bouncing in our level. And apparently, that's not what we want. But how can we get rid of that? Go back to it. So the module that we need to use is kill particles. So we need to kill these particles somehow when the collision happens. But the same question occurs, how do we know when that happens? Well, let's turn to this module for help. So if I click this show options and show parameter rights, then scroll down, click this drop down to show all the parameters this module is writing to. You can see there's actually quite a lot. And let's see if we can find something that can be useful. So if you go to the particles parameters, you can see there's this one, it's called has collided. This sounds like something we can use. So if we search for this, I'm going to go to here and type in has. You can see for this particle, this is a boolean. And this is perfect for our purposes here. So this is something that we can directly fill in inside of this kill particles. So I'm going to drag this parameter to here. Then go back to my level. You can see the bouncing issue is gone. Alright, I'm going to lower down their lifetime a little bit. So to something like 1 and 2. Alright, that's the first thing taken care of. Now that we know the exact timing of raindrops hitting the ground, all we need to do is use it. And same as location event, we can use generate collision event in here. So I'm going to add in that module. It's called generate collision event. And you can see after I bring it out, I get a warning message. If I go to the Niagara log in here, so this module, same as location event, it requires we take the persistent IDs. After our custom module effects, I'm sure you understand why we need to do this now. So go to properties, I'm going to take this required persistent IDs, and now the error message is gone. Alright, now this emitter is sending collision event, all we need to do is receive it. So for this rain splash small, I'm going to first add the event handler, and the event source, I'm going to change this to collision event. And execution mode, change it to spawned particles. Now for the spawn number, I'm going to give it a value of 1. And the max events per frame, I'm going to give it a number of 1 as well. So I don't want too many splashes in my level. If we keep this number at 0, we'll just see a lot of these splashes. Alright, I'm going to delete this spawn burst instantaneous because we don't need it now. Then I'm going to use the module receive collision event. And bring it out. Now go back to my level. You can see now we are spawning those little rain splashes, and this is not looking correct. We need to tweak its size a little bit. So go back to this rain effects. I'm going to change the size of this window and increase it to something like this so that we can see these splashes. So first thing, I'm going to go to this initialize particle and scroll down. So I'm going to use this float to scale these splashes. Right now, I think they're too huge. I'm going to try a number of 0.5. And I think this looks more reasonable. And I'm going to give this a random value. So change this float into a random one. And I'm going to use a value between 0.3 and 0.6. And you can see this is what I get. Already, we're getting somewhere. And the next thing that I like to adjust. So I think now their color is not correct. I want more transparency for these splashes. And we can adjust that. So I'm going to go to the color in here, double click to open it. I'm simply going to lower down this alpha value. So instead of a value of 1, I'm going to lower it down to 0.2. And you can see this is what I get. So maybe 0.2 is too much. I'm going to try 0.5. And the lifetime of it might be too long. So instead of 0.3 and 0.5, I'm going to lower it down to 0.1 and 0.2. And this is too short. So maybe 0.2 and 0.3. Alright, something like that. I'm going to keep tweaking this alpha value. So maybe 0.4 or 0.3. Like I said, on environment effects like this, it takes quite some tweaking until everything looks correct. So be patient in here. Don't rush it. And I'm going to click OK. I think this is good enough for now. I'm going to minimize this window. Maybe the size of it needs to be a bit larger. So go back to this initialized particle. I'm going to try a value between 0.5 and 0.7. Yeah, something like that. And that's pretty much it for this one. I think I'm quite happy with my end result in here. So this is the rain splash small that I just created. The key thing here is we need to use the collision event from our main raindrops to help us to spawn these splashes. Otherwise, we just don't know when we should spawn these. So for this one, we'll need the collision module. And because after using this module, those raindrops will be bouncing in our level, we need to use this module kill particles to kill them. And in order to get the correct timing for doing it, we can use a proberometer that this module is writing to, has collided. And after that, we just need to use this generate collision event to send the data we need to this emitter. And in this emitter, we simply need to receive it and spawn these particles. Other than that, it's just a matter of tweaking until everything looks correct. So this is the value that I use inside of initialized particle. You can use this as a reference, but again, don't hold on to it. Feel free to try out your own values. It'll take you some time to adjust these and the values inside of dynamic parameters. So hopefully you can have fun with this. And it's time to create your own rain splashes. I'll see you in the next lecture. Welcome! In the last lecture, we created these small rain splashes for our rain effects. And before we move on, I like to tweak some of its properties. So go back to my Niagara system. Inside of this initialized particle, same as this main raindrops, I'm going to give this color a random value. So change it to random range. Then copy this color, paste it to here. Then for the alpha, for the minimum, I'm going to give it a value of 0.1. For the maximum, I'm going to give it a value of 0.2. And also, I'm going to change this sub-UV animation. So right now, the default start frame is 0 and the end frame is 63. I think that's way too much. For this material instance, we only have 4 patterns. So I'm going to change this end frame to number 3. And go back to my level. And you can see this is what I get. Looks a bit more natural, I think. Maybe the lifetime of it needs to be increased a little bit. So I'm going to change it back to 0.3 and 0.4. Still feels not long enough. So maybe 0.3 and 0.6. And now I think it's too long. So I'm going to go with a value between 0.1 and 0.5. Alright, something like that. A little bit more variation for these splashes. And in this lecture, we are going to create different variations for these splashes by having some large rain splashes. And for that, first, we'll need to get hold of some textures. So go back to this realistic VFX textures. If you scroll down, there's this texture, it's called T_water_A. And this one, T_water_D. So I'm going to open them both, double click to open this one, double click to open this one. And these can be our splash variations. So this one can be a large rain splash, and this one can offer us more interesting variations. So I'm going to move these two to my own folder. So select this one and select this one. Move them to this rain effects folder, select copy here. And for this water underscore A, I'm gonna rename it to T underscore splash big. And this T underscore water D, I'm gonna name it T underscore splash variations. Alright, next thing, I'm gonna create 3 material instances for them. And just to save some time, I'm gonna directly duplicate this one. So press Ctrl+D to duplicate it. I'm gonna rename it to Rain Splash Big and delete the extra number at the end. Fill in the texture. So for the normal map, we can use the same one. And for the mask one, I'm gonna fill in this texture. And you can see this is what I get. I have too many tabs in here. I'm gonna right mouse button click and select close out the tabs. And I'm going to duplicate this Rain Splash Big, and I'm going to rename this to Rain Splash Variations and fill in the texture. So it'll be this one. Click this icon, and this is what I get. And all it's left there to do is we need to create 3 separate emitters for these material instances and start to tweak the values until they look correct. And that'll be our section challenge today. So the challenge is, I'd like you to create different splash variations for our rain effects, and same as the one that we already have, we need to spawn them using collision event, and of course we'll need to tweak the values of them until they look correct. Alright, pause the video now and give this a go, or come back if you need help. Welcome back! How did that go for you? Hopefully, at this point you already have those different splashes ready. Now let's look at how I would do it. So I'm gonna open this Niagara system, and just to save some time, I'm gonna directly duplicate this Rain Splash Small. So press Ctrl+D to duplicate it. Then I'm gonna change its name to Rain Splash Big. And go to Sprite Renderer. I'm gonna assign it this MI Rain Splash Big. And this is only one single pattern. It's not a flipbook texture. So for the sub image size, I'm gonna reset this value. Delete sub-UV animation module, and start to tweak its value. So first thing, I'm going to go to initialize particle. For its lifetime, this needs to be very short, because for rain splash like this, I don't think it should last very long. So for lifetime min, I'm going to change it to 0.05. Lifetime max, change it to 0.08. And I'll also need to tweak its alpha value in here. I'm going to do that later. Then go down to sprite size mode. I'm going to reset this and change this to a random uniform. So somewhere between 25 and 55 will work, I think. Alright, let's preview this in our level. So go back to my level. I'm just going to isolate this emitter in order for us to see better. And you can see this is what I get. I have some small splashes. So right now they just appear out of nowhere. I don't like that. I'm going to change that a little bit. So use the module scale sprite size. So I think I want a curve like this one. So I want a smooth transition for its side, and go back to my level to preview this. Now we can barely see this. That means we need to adjust the curve a little bit. So go back to it. For the timing of the second key, I'm going to lower it down to 0.1. And for its value, change it to 1. And preview this again. Yeah, hopefully you can see this. So now I have that little transition for these effects. Alright, I'm gonna cancel this isolation and preview it again. Something like that, looking pretty cool. And if you want more of these, you can go down to this event handler properties for this max events per frame. If you increase this value, you'll see more of the particles. So I'm gonna try 2 for now and preview it again. So maybe 2 is too much. I'm gonna lower it down back to 1. Alright, something like that. And next thing, I'm gonna use this material instance. So I'm gonna click pause in here. Then go to File, click Save All. Select this Rain Splash Small. Press Ctrl+D to duplicate it. And change its material instance to Rain Splash Variations. And just to quickly remind you, this is a flipbook texture. And this is a 4x4 texture. Go to this sprite renderer. I'm gonna change this to 4x4. Then I'm gonna start from the top. So instead of initialize particle, change this to random uniform. And I think I'm going to start with a value of 50 and 60 and see what this will look like. And for its lifetime, I'm going to change it to something like 0.3 and 0.5. And I'm going to rename this emitter to Rain Splash Variations. Alright, I'm gonna preview this. And just a little bit of extra details. I'm gonna go back to it and I'm gonna isolate this emitter. And for this sub UV animation module, so I'm gonna reset this back to 63 and preview this emitter only. So you can see this is the effect that I get. Right now I think they jitter too much, so I'm gonna increase their lifetime. Instead of 0.3 and 0.5, I'm gonna try 0.8 and 1. Yeah, this looks a bit better. I think for the sub UV animation, the end frame needs to be correct. Otherwise, this is looping too much. So go back to it. So the texture itself, this is a 4x4 texture, meaning there are 16 patterns. So I'm going to change the end frame to 15. And you can see this is what I get. And now the lifetime is too long. So I'm going to lower it back to 0.3 and 0.5. Yeah, something like that. And the size of it is too huge. So I'm going to lower it down to 35 and 45, maybe 55. Alright, cancel the isolation. And you can see this is what I get. Yeah, it's adding a little bit of extra details to our splash effects. And I'm going to start to tweak the dynamic parameters for these two emitters. So for this rain splash big, go to this module, scroll down. The first thing that I'm going to adjust is this Fresnel strength. So I think I'm going to try a value between 3 and 4.5 for this rain splash variations. Fresnel strength, I'm going to try 4 and 5. Maybe 3 and 4. And lower its lifetime a little bit. So to something like 0.1 and 0.3. Maybe 0.2 and 0.5. And for its alpha, minimum 0.1 is fine, I think. Maximum, I'm going to lower it down to 0.15. There are really no specific reasons for me to adjust the values. Try out your own values until you have something you like. And I think I'm quite happy with the end result in here. I wonder what your rain effects looks like now. Do share it in the Discord channel. I can't wait to see what you have come up with. So these are the two emitters that I just created, and use them as a reference if you need. There's really nothing too fancy about them. It's all the same as the ones that we've created. It's mainly about tweaking the values until they look correct. Great job! I'll see you in the next lecture. Welcome! In the last lecture, we created different splash variations for this rain VFX, and this is what we have so far. And there's one more emitter that I like to add to this Niagara system, and there will be some ripples. So first, let's get hold of some textures. I'm going to go back to this realistic VFX textures. If you scroll down, you can see there's this texture T_splat, and this is the one that we can use. So I'm going to copy this one to my rain effects folder, select copy here. Then I'm going to change its name to T_ripple and double click to open it. You can see this is what this texture looks like. Note that it doesn't have alpha channel. So for the mask, we can use either red channel or green channel. It doesn't matter. And the current setup of our liquid master material will just work. Alright, I'm going to create a material instance for it. So go back to my content browser. I'm going to duplicate this material instance and I'm going to change its name to ripple and double click to open it. And I'm going to fill in the texture. So it'll be this T_ripple. Fill it in here. And I'm going to untick this. It's mask stored in alpha. And you can see this is what we get. Now I'm going to add this to my Niagara system. Go back to my rain effects. Just to save some time, I'm going to duplicate our existing emitter. So I'm going to use this rain splash big. Select it, press Ctrl+D to duplicate it. And I'm going to rename it to rain ripples. Then change its material instance. So it'll be this mi_ripple diparam. And I'm going to isolate this emitter and go back to my level to see what this looks like. And right now I cannot see anything. That's because the size of it is too small, I think. So that's the first thing that I'm going to adjust. And I'm also going to change its lifetime. So lifetime min, I'm going to start with the value of 0.5 and lifetime max, change it to 1. For the sprite size min, I'm going to start with a large value, something like 200, sprite size max, change it to 250. And for this color mode, I'm going to reset it to default and increase its alpha value to 1 and preview it again. And you can see this is what I have. So maybe the size of it is not large enough. So I'm going to try 300 and 350. Yeah, something like this. So the first issue that we need to solve is the phasing issue. Since these are sprites, no matter where we are in the level, they will be always facing our camera. And this breaks this effect completely. And to solve this issue, we need to manually override the sprite facing direction. And we can do that by first going to Sprite Renderer, change the facing mode to Custom Facing Vector, and inside of this particle spawn, add in the module Sprite Facing and Alignment. So for the facing, I'm going to give it a value of 1 in the Z, so these sprites will always be facing up. Then preview them again. Alright, this is what I want. And the next thing that I'm going to adjust is the Scale Sprite Size module. So usually for an effect like this, its size should increase as it ages. So for that, I'm going to change this curve. Go back to this Scale Sprite Size. I'm going to change this curve to this one. And preview again. And right now, I cannot see anything. That's because the starting size of this emitter is way too small. So for the first key, the value here, instead of 0, I'm going to increase it to 0.5. And you can see this is what I get. Now the size of it is way too large, but you get the idea. Now I'm going to lower them down. So go back to initialize particle. For the uniform sprite size, lower it down to 200 and 250. Then I'm going to disable isolation and see what this looks like. Alright, I think they're still way too large. So keep lowering down the size to something like 100 and 150. Then I'm going to lower down its alpha value to something like 0.2. And I'm going to keep tweaking its size. Right now it's way too small. Alright, so my final size for it is between 200 and 210. Try all your own values here. And for the color here, I'm going to lower its alpha down to something like 0.05. So a really low value, and click OK. Yeah, something like that. It adds more interesting details to this VFX. And there's one issue that we need to solve. Maybe you've already noticed that. So you can see the spawn location of these particles, they are not exactly accurate. So some are correct, some are a bit off. And the reason for that is, if we go back to this Niagara system and go to the collision module, the collision radius is the reason for why that's happening. So how the collision is calculated is based on this particle radius scale. And right now the scale is too large, so some of the collision events will happen above the ground. I'm going to lower down this value to something like 0.4 and preview this effect again. And now you can see it becomes much better. Alright, something like that. I think I'm quite happy with my end result in here. Currently, this effect looks great, but we have another issue. To quickly show you what that is, I'm going to go to my third-person folder, and inside of this folder, level prototyping, there's the mesh that we need. So go inside of the meshes folder, I'm going to drag out this sm_ramp. Then I'm going to adjust the size of this ramp, so increase its size on the y-axis, and make it a bit bigger to something like this. And now I'm sure you can see the issue. So for all these ripples and rain splashes, if we spawn them on the flat ground, they look alright. But apparently when we spawn them on the slope, this is completely off and it breaks this effect completely. So we need to find a way to eliminate these particles on the slope in order to have a better VFX. And we'll need to create another custom Niagara module for it. In the next lecture, we'll look at how we can do that. So this is the emitter that I just created, and there's no difference between this one and the ones that we created so far. So it's mainly about tweaking the values in here. Alright, time to create your own ripples, and I'll see you in the next lecture. Welcome! In the last lecture, we created these ripples for our rain effects. Right now, the main structure of this VFX is done, but we still have one more issue to solve, and that is the slope issue. So currently, you can see the collision events will happen on the slope, and that's fine, but the particles spawned based on it are completely off, so we need to take care of this issue. And the first solution that I'm going to use, so I like to kill all the particles on the slope and keep all the particles on the flat ground. How can we do that? Well, apparently, if we want to eliminate the particles we don't want, we need to get hold of them first. The thing is, how can we accurately filter out all the particles we need? Well, let's turn to our collision event for help. So I'm going to open my Niagara system, and I'm going to go to any one of these emitters. I'm going to select this rain splash small. So if you go to this module, receive collision event, you can see inside of it, there are a lot of properties. And let's go to this position. So it has a parentheses inside of it, it says vector 1, and currently this is set to be applied. So this is the position data sent by the location event sender. And if we say to be applied, you can see here it says it will write the received event position to particles.position. So this is how the collision event is achieved. This particle position coming from the sender is directly writing to the receiver. That's why we can spawn these particles based on the source emitter. And there's another option. So here it says we can also change it to output. If we do that, this will output the received event position to output receive location event vector_1 for use later in the event stack. So if we change the option to output this value here instead of directly writing to particles.position, we can store it and use this later. And if I go to the search bar here and I search collision, you can see for the module receive collision event, there are 3 vectors here, and if we change this option here to output, the value here will be stored inside of vector_1. So that's the meaning of a parentheses vector 1. But how is this going to help us to get what we need? Well, this is everything. So if you look at the second option, here we have collision normal. So when the collision event happens, we will know the surface normal of the colliding spot. And currently it's set to be applied. If we change this to output, the value here will be stored inside of this vector 3, so this one. And we can use this value to help us to get hold of the particles on the slope. But how are we going to do that? Well, let's take a look at this. So I'm going to use this sphere as the example mesh. When the raindrop hits the slope in here, we can know it's surface normal. And if we perform a bit of math calculation in here, if we will use the dot product to compare this vector with the up vector, then we can know is this the particle on the slope. So the math behind dot product, when we are comparing 2 vectors, it will return one float. If these 2 vectors they are parallel with each other, the result will be 1. If they are perpendicular, the result will be 0. And if they are the exact opposite, the value will be -1. So if I use dot product to compare these 2 vectors now, what's my result going to be? I'm going to pause here for a few seconds, think about the answer. So if the vector is parallel with this up vector, we'll get 1. If it's perpendicular, we'll get 0. And this vector is between this one and this one. So we should get a value between 1 and 0. And the math we need here is we can simply do an if check in here. So say if the return result is greater than 0.99, that means this vector must be parallel with this up vector, or at least almost parallel. And if this is true, then we want this particle to live. And if this is false, that means this is the particle on the slope, then we want to kill it. And now we just narrow down the things we want into this one single boolean. So let's look at how we can set this up. Go back to my project. So first, I'm going to create a new Niagara module. So go to Effects and select Niagara module script. I'm going to rename this to nms_check collision normal. And double click to open it. First thing, change its category to custom. Library visibility, change it to exposed. Keywords, change it to check collision normal. Alright, the first thing, I'm going to give it a function input. So this function input, it needs to be a vector. And later, we can directly use the stored collision normal as this input vector. So I'm going to call this collision normal to check. Alright, the next thing, I'm going to drag out a pin. Then I'm going to use dot product And you can see we have it right there, that product of two vectors. And the second vector that I'm going to compare, so it'll be an up vector. And for that, we can directly make a vector inside of Niagara. So type in vector and select this one. For the up vector, it simply needs to have a value of 1 in the z-axis and plug this into socket B. Alright, I'm going to check this return result. So if this result is greater than 0.99, then here this will return true. Alright, in here I'm going to make a float for it. So type in float and give this value 0.99 and plug this into socket B. Now we just got hold of the boolean we want. Then for the map set, the values that I want to set, for killing the particles, there's an existing parameter that we can directly use, and that one is called alive. And you can see it's right there. It belongs to the namespace data instance. Remember our module kill particles? So that module is setting this same parameter as well. If this is true, our particle will live, and if this is false, our particle will die. So I'm going to directly plug this into here. So if this is true, our particle lives. This is false, then our particle will die. Alright, I'm going to click apply, then go back to my rain effects. I'm first going to isolate this rain splash small and go back to my level. So you can see this is what I get. I have some small splashes on the slope. And now let's check if the module that we created will work. So go back to it. I'm going to add in the module NMS, check collision normal. It needs one function input, so this collision normal to check. And for that, we'll first need to go to this receive collision event and change this collision normal from apply to output so that we can store this value inside of this vector underscore 3. Then we can assign this vector underscore 3 to this function input. And now if I go back to my level again, you can see I don't have particles anymore on the slope. Alright, I'm going to assign this module to every one of these emitters. So first go to receive collision event, change this from apply to output, then copy this module, paste it to here. Then go to this one, this rain splash variations, change this from apply to output, then copy this module, paste it to here. And the last one, change it to output, paste the module in here. Alright, now I'm going to cancel this isolation and go back to my level. And that's it. You can see we no longer have particles on the slope, only on the flat ground. How cool is that? So the solution that we just used, it works, but it's just not a very good one. So basically what we did was, if something doesn't work, then we don't use it. A better solution for this is, instead of directly killing these particles, we should change their alignment so that they'll align with the surface that they're colliding with. If we can do that, we'll have a much better rain effects. But what if I want to leave this option to users? So inside of this Niagara system for this custom module, what if I want to drop down here for whoever is using this module? They can select whether or not they want to kill the particles or align the particles. Well, with Niagara, we can do just that. And we'll look at how we can do that in the next lecture. So these are the nodes that I just used. This is just some simple math calculation, and the result we can get is quite amazing. Alright, it's time to create your own, and I'll see you in the next lecture. Welcome! In the last lecture, we created a custom Niagara module for us to eliminate the particles on the slope. And this is the result I get, so we don't have particles anymore on the slope. And in this lecture, let's look at how we can add a drop-down to this input of this module in order for us to control how this module should behave. And to do that, we'll need an enum. What is an enum? If you come from the programming background, this should be no problem for you. And if you aren't, I can just show you a few lines of code and walk you through how it works and why we should use it. Or I can simply just tell you, this is the thing that we've been using the whole time inside of Niagara. Remember this? This is our shape location. Remember this? This is our initialized particle. And remember this? This is the transform for us to adjust our shape location. All these drop-downs here, they are enums. So for an enum, You can think of it as options inside of a dropdown. If you recall, by changing the options inside of these dropdowns, we can get total different function inputs. So currently, this is box and plane. If I change this to sphere, in here, we can control the sphere radius. Currently, the column mode here, this is set to be direct set. If we change this to random range, the function input will change as well. And that's what enum can do for us. It can provide us with different options, and based on the selection we make, we can get different results. Unlike a true or false boolean, which only has 2 scenarios, an enum can have multiple scenarios, and what's best about it is we can give names to these different scenarios. So enum is in short for enumeration. These options, they are just numeric values, but we can give these numeric values different titles. And when we want to use them, it'll be very clear for us to see what we are doing. Alright, now that we know what an enum is, let's think about what we want to do here. Let's say I want to create a new enum, and I'm just simply going to call it collision check mode for now. For this enum, I like to give it 2 options. So option 1, kill particles on slope. Option 2, align particles with slope. Let's go with option 1 first. So the input of our module stays the same. It will be this normal input, so normal to check. And if this is the option that we select, so we need to do the dot product. And based on the return result of that product, we can kill the particles. So this is the thing that we did in the last lecture. And if we change this check mode from this one to align particles with slope, then the things that we want to do here, we're going to use this collision normal to set our sprite alignment. And by doing this, we can achieve what we want, which is aligning all those splashes, ripples with the surface. And hopefully you can see the issue here. So in here, we have 2 parameter maps. In the first parameter map set, we are using the dot product and setting the parameter alive. The second parameter map, we are setting the sprite alignment. But in Niagara module, only 1 parameter map set can go to final output. So finally, we can use a switch node in here and switch on these different conditions. If this is the condition we set, this parameter map set will go to the final output. If this is the one we choose, this parameter map set will go through. So this is the logic that we're going to use later. And our final missing puzzle is, how do we actually create a custom enum for Niagara? Well, there are a few steps that we need to take. First thing, of course, we need to create an enum for it. This is the same as creating an enum for Blueprint. We can directly do it inside of Unreal. Then, unlike using an enum in Blueprint, we need to add this newly created enum to Niagara enum list in project settings. So this step is a bit special. And after that, we can use switch node in Niagara and switch on this newly created enum. Alright, let's look at how we can do this. Go back to my project. I'm going to first right mouse button click and go to Blueprints. Select this enumeration. Select it. For its name, I'm going to name it Niagara Custom. So the prefix that I use here, all the enums in Unreal start with E, and all the enums in Niagara start with E Niagara. And the custom here is, I just want to distinguish this one from all those existing enums that Niagara uses. Alright, next thing, I'm going to type in underscore, and I'm going to call this enum collision normal check. And double click to open it. So we need to add some options to it in order for this to work. And to enum, this is called add enumerator. So I'm going to click this button. This is the first option that we're going to see later. So I'm going to call this first option kill particles on slope. Alright, I'm going to click this button again. And the second option, I'm going to call it align particles with slope. Alright, and click save. Now we have this enum ready. Next thing, we need to add it to our Niagara list. So we can do that by going to this project settings. And inside of the search bar here, type in Niagara. And if you scroll down, you can see there's this option, this drop down for additional parameter enums. So we can click this add button here and add in our newly created enum. So I'm going to type in Niagara custom. And you can see this is the one that I just created, collision normal check. I'm going to select it, and every time we make some changes inside the project settings, we'll need to restart our project. So I'm going to close this window and close my project. Then I'm going to restart my project. Alright, go back to my project. I'm going to go back to this custom Niagara module. And in here, I'm going to first bring out the switch node. So right mouse button click and type in switch. So it's called static switch. And in here, we first need to define the static switch type. By default, it's set to be bool. So we can click this drop down in here. And if we browse through these options, you can see this is the one that we just created. This enum, Niagara custom. For some reason, we have two added to here. I'm going to select the first one. This shouldn't matter too much. You can see for Unreal's enums, it has the same issue. So I'm going to select the first one in here. And I'm going to increase the size of this tab a little bit. And now you can see the default value here. This is the value that we just set. And the first one, this is called input parameter name. So this is the name next to the dropdown that we can see. I'm going to change this input parameter name to collision check mode. Alright, that's the basic setup for this static switch. And the next thing, if you recall, in order to achieve what we want, we need two of this. So we need two map set. So in Niagara, we can have as many map set and map get as we want. So I'm going to click this add button in here. So this will decide the output type of this static switch node. And in this case, it'll be Niagara parameter map. And you can see if our option is kill particles on slope, one Niagara parameter map will go through. If this is align particles with slope, another will go through. So I'm going to move this node to here, move this one to here, and place this node in here. So if the option is the first one, this map set will go through. Connect this pin to here. And if the option is number 2, then we need to create a different map set. So right mouse button click, I'm going to type in map set. And the value that I want to set here, so we no longer want to kill the particles, we want to set their sprite alignment. And that's an existing parameter. We can just directly type in sprite alignment. And you can see it's right there. I'm going to select this one. Then I'm going to move this node down. And I'm going to go to this map get. And move these nodes out a little bit. And organize my graph, move these up. Then I'm going to connect this pin to here. And drag down this pin to here. So for the things we want, we only need one map get since the function input is the same. We can also create different function inputs, and by selecting the options here, different function inputs will be exposed to us. So go check that out if that's something you want. And also I'm going to connect this input pin to here and organize it. Drag it down to here. And the last thing, I'm going to connect this one to this pin. And that's pretty much it. Now I'm going to click apply and go back to my Niagara system. And I'm going to click this MMS check collision normal. You can see now we have one more option in here, collision check mode. If I click this drop down, I have two options that I can select. Alright, I'm going to select this align particles with slope. And in case you forget, we just set the sprite alignment. That means inside of this sprite renderer, we need to change its alignment from unaligned to custom alignment. Sadly, this is not something that we can set directly inside of Niagara module. This is something that we need to manually set in these dropdowns. So I'm going to set this for all of these emitters. So this one, change it to custom alignment. This one as well. And this one, change it to custom alignment. Alright, go back to my project. Now I'm still not seeing the particles on the slope, and that's because I'm going to go back to my Niagara system. For this MMS check collision normal, I need to change this collision check mode. Right now, these particles are all being killed. So I'm going to change this to align particles. Change this one. And change this one. And make sure this one is using this check mode. Alright, go back to my project. And now you can see this is what I get. Now all these splashes ripples, they are aligning with our surface. How cool is that? With some simple math calculation inside of our custom Niagara module, this is what we can achieve. And I'm sure you can notice that, so all these splashes, they're currently aligning, but for our ripples, they're still facing up. And the reason for that is, I'm going to go back to my Niagara system, go to this run ripples. So inside of this sprite facing and alignment, we're controlling this sprite facing in order for these ripples to face up. So changing the sprite alignment here won't work for this one. And in this case, I'm just going to change this align particles to kill particles on slope. So we won't be able to see any ripples on the slope. and go back to my project. And you can see this is what we get. Of course, you can set up some extra logic to set the facing of the ripples to be the collision normal. In that way, you'll have the ripples with correct facing. But I don't think we should have ripples on the slope, so I'm not going to do that in here. And this is what we get, our final result for rain effects. Looking pretty cool. And now looking back at the effects that we just created, hopefully this one can show you all the possibilities with Niagara that we have. With every module customizable, there are countless things that we can do and countless interesting features effects that we can make. You can find the module that I created in the resources dropdown of this lecture, so if you get stuck later, double check if you have missed anything shown in the lecture. And you can download the one in the resources dropdown for some reference if you need. And we're going to create more stunning effects in the lectures to come. I'll see you in the next lecture.